Hello everyone. Today we will present our research about use of face emotion recognition on four-wheel vehicle to analyze driver condition. We are from group 14 and we will introduce our group member. First we have,
Alberto Kadir.
and second myself Chico Alberto Gilardino, and third we have,
Ernest.
okay, next. Okay, we have abstract. Um, Distraction while driving is still a global problem that causes thousands of accidents and deaths on the road every year. One example of distraction while driving is a driver who drives in unstable condition. To reduce the frequency of accident, this study discussed facial emotion recognition, which is applied in four-wheel vehicle. The study explored an AI-based approach using facial emotion recognition to detect driver condition through dashcam recording, which of course can overcome accidents that often occur due to unstable driving condition. With FER technology, using CNN LSM model, it can analyze facial expression, eye movement, and other behavioral cues in real time. The study focused on analyzing driver facial recognition accurately so that it can distinguish the condition of the driver in a conscious, sleepy, tired state so that it can reduce the risk of accident when driving. In addition, this study also maintained the privacy of its users by preventing misuse of user facial data so that user can use these technologies safely and comfortably. And also, this research is one form of contribution to the development of technology, especially in the automotive sector. We're currently entering the era of intelligent transportation that use AI assistance to improve efficiency and safety in driving. Next. Next introduction. Traffic accidents are one of the world problems that often occur today. One of the cause of traffic accident that often occur is because the driver is driving in an unstable condition, such as the driver is sleepy, tired, and stressed. Therefore, to reduce the frequency of traffic accident, we can utilize FER technology that can detect the condition of the driver when driving in real time. This technology utilizes the CNN algorithm and LST algorithm. CNN is itself play a role in extracting facial feature in order to detect the condition of the driver, while LSTM play a role in analyze the pattern of change in facial expression over time. By utilizing this technology, it can reduce the frequency of traffic accident caused by driver who drive in unstable condition. In addition, by implementing and developing this research in the automotive industry, it is one form of contribution to improve intelligent transportation system that can improve driving safety. Next. For the third review, we have driver emotion detection using CNLSTM. Various facial recognition techniques have been widely studied to support the accuracy of the FER system. FER technology to detect driver condition use CNN LSTM algorithm. Second, we have multimodal approach in driver emotion recognition. This study used a multimodal approach, namely combining motor activity data and driver facial data to detect driver condition. And we have model architecture CNN LSTM. The CNN serve a deep learning architecture framework that is notably successful for image analysis tasks such as facial expression recognition. And the LSTM is a form of recurrent neural network designed to solve the vanishing gradient issue with the help of memory cell and gating mechanism. Next.
Hello everyone, I'm Nathan and I'm going to talk about research methodology. This research methodology is systematically designed to build and evaluate a deep learning model capable of analyzing driver conditions. The stages of the methodology include independent data collection, pre-processing for standardization, dataset sharing and balancing, model architecture design, and training and evaluation process configuration. As for data collection, we made custom datasets ourselves, and there are 6 facial expressions, which is angry, fear, happy, sad, sleepy, and surprised. From each recorded video, 10 consecutive image frames were extracted to form a single data sequence, which will be used to train the model to recognize temporal expression patterns. As for the data preprocessing, each image frame is converted to grayscale format, and its size is standardized to 112 times 112 pixels. and the pixel values are normalized into the range of 0 and 1 by dividing each value by 255 to stabilize the training process. The process frames are rearranged into a sequence with the final shape of number of frames 10, the height 112, the width 112, and the color channels of 1. Next. As for the data sharing and balancing, the dataset is divided into 80% training data and 20% testing data. This process uses a stratification method to ensure that the proposition of each emotion class remains balanced in both datasets. To deal with the uneven number of samples, a class weight balance strategy is applied during training to give a higher loss weight to the minority class, so that the model can learn to recognize all classes more fairly. As for the training and evaluation configuration, the model was compiled using the Adam optimizer and the categorical cross entropy with learning rate 0.0005. The training process was monitored with model checkpoint, early stopping with the patients of 15, and the reduced learning rate on plateau callbacks. Model performance was evaluated using accuracy, precision, recall, F1 score, and confusion metrics. Next. For the result discussion, the overall performance of the model runs efficiently and stopped at the 51st epoch out of a total of 100 planned epochs. This process is automatically stopped by the early stopping callback, indicating that the model has reached its optimal performance point on the validation data and has successfully prevented overfitting. The final evaluation on the test data shows very satisfying results. The proposed model managed to achieve an overall accuracy of 92%. This high level of accuracy proves that the model architecture is able to generalize well on data that has never been seen before.
For result discussion, we have the classification report table in which angry is 0.5, happy 0.94, and sleepy 0.92. That's the highest F1 score. For the precision score, we have happy and sad that got perfect accuracy, reflects high model confidence and 0 false positive. And perfect recall. For angry and sleepy, we get a perfect recall, so that means that all two samples are detected. Sadly for the case, we have sad class. Although the precision is 1, that is highly accurate, the recall is 0.78, which means that the model only detects 78% of the image, and the other 22% were missed and possibly predicted as other class. You can observe this in the confusion matrix after this. And for the angry class, same as the sad class, we have 1 recall, but we have less precision, which is 0.91. That means that the model misclassified a small portion of the test data. For the confusion matrix, we have strong overall performance. Most prediction lie on the main diagonal of the matrix, as you can see. For class specific highlight, angry got 9 out of 10 sample correctly classified, and sleepy got 12 out of 12 correctly classified. This shows critical accuracy for detecting drowsiness in driving scenarios. Although some common misclassification pattern that was explained before, 7 out of 9 correctly identified. 1 misclassified as happy and 1 as surprised. In conclusion, misclassifications are minimal and explainable. Overall, the confusion matrix confirms the reliability and robustness of the model. Maybe in the future, if we add more data and have stronger GPU, we can redo the testing and make the model better. Conclusion. The study successfully designed and trained, deploy a custom CNN LSTM-based model architecture for classifying driver state emotion from sequence data. Result may vary, but it successfully achieved an overall accuracy of 92% on test data, which in particular shows strength at sleepy and angry with 100% recall. The limitation. The main limitation of the study lie in the source and amount of data. The dataset used was created independently and has a small sample size for deep learning model. Although the class balancing strategy has helped, it may limit the generality of the model to diverse real-world population and condition. Here are the references for our project. Thank you very much for listening.